This meeting is being recorded.
In section 2.7, we're going to review this concept of resonance with respect to organic chemistry now. So we're going to focus on organic molecules and specifically in this case, a certain type of carbocation. So this is called an allylic or an allyl carbocation. So what that really is we have a double bond and then a alternating with a single bond here. So that's an allylic portion. And then because this formal charge here on this carbon is +1, we call it a carbocation. So what we have here is on each of these carbons that are numbered 1, 2, and 3, there's a p orbital, right? That is, we'll see this on the next slide, so I won't draw it, but there's a p orbital, an empty p orbital on each of these carbons. So what happens is this pi bond, right, that we see with p orbital overlap here, is delocalized. So what that means is that we're going to see a more even distribution of both electrons amongst all these carbons and this +1 formal charge. So let's take a look here at the p orbital overlap that results. So these are all unhybridized p orbitals. So each of carbons 1, 2, and 3 in our structure have an unhybridized p orbital, and these would be able to overlap when that's side-by-side overlap, and this allows that free movement, right? That overlapping allows the free movement or delocalization of electrons. They're not local to one atom, they're delocalized or spread out over the whole molecule. And another way of saying this is that a molecule has resonance. And we'll look at this depiction in a Lewis structure form in a couple slides, but that's the resonance that you may recall from general chemistry, that we show two accurate or correct Lewis structure depictions that are incorrect to show a hybrid or model of what is correct. So let's take a look here at an introduction in molecular orbital theory viewpoint. So we have 2 pi electrons in our bond here, right? Let's go back here. So we have the 2 pi electrons from the p orbital overlap in this double bond. We know we have hybridized orbitals that are involved in the sigma bond between the 2 carbons, but we also have this pi bond, right? This p orbital overlap. So those 2 pi electrons would occupy the lowest energy molecular orbital, which would be a bonding molecular orbital. So we look at this structure here, and we see that a bond would occur, right, with this these 2 pi electrons. And when we have an allylic carbocation, if we think of it in terms of molecular orbitals, you can kind of see more clearly that electrons are free to move, and also that +1 charge could also be more evenly distributed amongst the whole molecule. And not just one carbon atom would have a positive charge drawn. So another way of representing this allylic carbocation is with 2 different resonance structures. So what hopefully you remember from general chemistry is that neither of these 2 structures actually represent this compound accurately. The compound is not going back and forth, shifting from one structure to another. It's actually a combination or a hybrid of these 2 allylic carbocation depictions here. So we can draw it in this way as a resonance structure, or we can draw what's referred to as a hybrid. So this shows that double bond, that pi bond is evenly, those pi electrons are evenly distributed amongst the whole molecule. And we also, instead of having a formal charge on one carbon atom, we have this partial or lowercase delta plus symbol here, partial positive charge, spread out amongst the whole molecule. So sometimes you might even see something like this as well, with a positive charge just evenly distributed in the middle. So there's a few different ways of representing resonance. And what can we tell from resonance? What does resonance indicate? So what resonance indicate or should indicate to you is that since we have these delocalized electrons, they're more spread out, this results in a lower energy. And we had discussed in a previous video that lower energy, right, lower potential energy would indicate a more stable compound. So resonance, in turn, will stabilize a molecule. So if a molecule has resonance possible, whereas it has delocalized electrons versus formal charges on atoms, um, those molecules that have resonance will be more stable versus the formal charges. So, right, these electrons have more freedom, minimalizing any repulsions. What else? They spend time to multiple nuclei, so positive and negative charges would attract. And that delocalization of charge, as I mentioned, that spreading out of that +1 charge results in, again, a more stable compound. So that's everything from section 2.7. We will continue with 2.8 in the next video.